Okay, so we're continuing our proof of the cone theorems. So last time we proved, uh, we proved that the non-vanishing theorem implies base point free theorem. So let me just recall both. So if x comma delta is projective KLT, and D is a Neff Cartier divisor, with the property that AD minus KX plus delta is big in Neff, for some A. Then D is semi-ample. Okay, meaning that some large enough multiple is base point free. And then last time we showed that the non-vanishing theorem implied base point free. Um, and the non-vanishing theorem, very similar setup. I'm just going to summarize it a little bit. So we have some KLT pair x comma minus g, where now minus g doesn't have to be a boundary. So it doesn't have to necessarily be effective. But at least this pair is KLT. And D is a Neff Cartier divisor, such that basically same assumption. So this difference of AD minus the log canonical is big in Neff. Then we have sections for all large enough multiples. And I'm going to start using, just for convenience, this notation where I'm not going to always write OX of a divisor, but it'll be implicit that if I write H0 with coefficients in a divisor, I really mean with coefficients in its associated sheaf. So that this is not equal to 0 for all m greater than 0. Okay, so that's the non-vanishing theorem, and you should note the assumptions are essentially the same, except for this fact that G does not have to be a boundary in the non-vanishing theorem, while in the base point free theorem, delta really has to be a boundary. So in particular, it's effective, and in that case, we get this semi-ampleness, and in this more general case, we just have that there are sections. So I want to make one more remark in that vein. So this roundup, because we're assuming that x comma minus g is KLT, then that tells us that this roundup is actually effective. But if g is a boundary, sorry, if minus g is a boundary, then in fact the roundup has to be 0. And so in the non-vanishing theorem, if we are assuming that our pair has an effective boundary as our divisor, then there is no roundup in this statement. It's just 0, and then we get that MD itself has sections, which of course is what you need. You need at least sections to have a base point free linear series for D, but you need a lot of sections to have a base point free linear series. So you should think of it, that's the difference between the hypotheses of these two, that in general we get sections when we add some effective piece, namely this roundup, and in the case where delta is a boundary, D itself has a lot of sections, or a larger multiple of D itself actually has those sections. Okay, but also this fact that the roundup is effective will come up multiple places throughout the proof, so I wanted to really emphasize it here. Okay, so I said this in words, but I'll just say it again. What we showed last time was that non-vanishing implies base point free. Okay. So this time we want to employ exactly the same strategy, which I'll recap in a second, to prove non-vanishing. Are there any questions about the statements for now? Okay. So let me just recall the strategy that we employed before, and it'll actually be the same strategy again for proving the rationality theorem. So it's a powerful strategy. So let's say we have some pair. I'll write delta just for convenience, but like I said here, technically, I usually use delta to mean a boundary, while here -g isn't a boundary, but for the strategy, that's not so important. So we have our projective KLT pair x comma delta. So we wanted to use induction to produce these sections, and to induct on the dimension, we want to be able to restrict to some divisor, and then be able to write down on that divisor that everything that our restriction satisfies our hypotheses. And to do that, we need to be able to use a junction. And so the idea is to find some expression. Sorry. Let me write this. So take a resolution and we want to be able to write down on this log resolution some expression where we can use a junction to restrict. And so last time we went through kind of the argument to get to this point, but what we said was that if we can write down an expression of the form bf upper star d minus ky is equal to n b comma c plus f, I'll write it as plus delta y minus e, where in last time we separated the delta and the e, this time these will come up as just a divisor a, but where this is some smooth irreducible reduced divisor. Here n, we want n to at least be big enough because we want to apply our commutative vanishing theorems, but actually it'd be better if we can take n to be ample, because we also want to use our induction to restrict to f, and so we need to know that this big enough property of n persists when we restrict, and the best way to do that is to just have it actually be ample instead of just big enough. And then E was effective exceptional. And then delta is some KLT boundary that we have floating around that's basically just everything else, so that we can apply our vanishing theorems. Okay, so we want an expression like this. And given such an expression, then we can write down ky plus f plus this big N f n is equal to b f upper star d. Now on the other side we have plus e. Let me just write it. I said that in this case it'll be easier to think of it as just a. So let me just write it all as. Let me call this minus a. So on the other side we have plus a. And now when we restrict to f, so I forgot one more property that we wanted f to satisfy, which is that if f shares no components with n, that's also important. Then when we restrict, we get by adjunction we get kf plus this n, where because n was ample, then this is also ample, and so this is equal to whatever bf upper star d plus a restricted to f is. And now our inductive hypothesis gives us sections for the left-hand side. And so the right-hand side has sections, but also, so our first observation is the left-hand side has sections, and our second observation was that comma of Vivek vanishing gives us that h1 on y, ky plus n is 0. And so that tells us that that the restriction map is surjective on sections. So BF upper star D has sections, plus A has sections on Y, but now we really care about F. We really care about D. We really want to go back to X, and now 3. We arrange it so that well, I guess I skipped one step here. I really want to round everything up. So we have this equality, and then k is integral, f is integral, d is integral, a and n are not necessarily integral, so I want to round everything up. So that makes sense to talk about sections of this divisor and not some twist. Okay, and then the last step was we arrange everything so that the roundup of A is effective exceptional up to G. So in the base point free theorem, we just needed it to be effective exceptional because we were talking about D itself. In the non-vanishing theorem, we needed it to be effective F exceptional plus roundup of G, because we have this roundup of G in the statement of the theorem. And so that tells us that the sections are the same as the pullbacks from, sorry, here I should say plus the pullback of the roundup of G. So whenever we have this divisor of the form pullback of something plus effective exceptionals, then the sections are the same. This is our negativity lemma that we used over and over again, which tells us that our sections on Y of this pullback are the same as the sections on X before we pull back. Okay, so that was our general strategy. And the only difference between this case and the base point free case is that we have this extra G here, and that's just going to be absorbed in how we define all these various divisors N and A. But this is, yeah. Okay. And then the other thing is, how do you arrange that you can write things this way? And you have to use the divisors given to you in the situation. So last time we said write, split D up into its or maybe some large multiple of D into its moving and fixed parts. And then we need some discrepancies to balance things out, because on one side we have just ky and a pullback from D, but really we know something about kx, not about ky. So we need to have some contribution from discrepancies. And then we also perturb by a small generic relatively ample. My pen keeps disconnecting. And this perturbation served us two purposes. It made N actually ample rather than just big enough by adding this perturbation everywhere. And then it also allowed us to guarantee that F was smooth irreducible and sharing no components with these divisor N and these other pieces that we need to restrict. Okay, so that's the general strategy recapped again. Are there any questions? Okay, and one thing I should make clear, the reason that we wanted F to be disjoint from these other, not disjoint, to not share components from these other divisors appearing, is exactly so that when we restrict, the restriction still is a nice kind of normal crossings divisor, and that roundup commutes with restricting. Because you can imagine if they do share some components, maybe they have some negative self-intersections and they completely change. After you restrict, you completely change the coefficients, and so this N doesn't have to be an ample. Well, it's still ample, but it doesn't have to be a normal crossings boundary, and the roundup doesn't have to be the same as the restriction of the roundup. So we can't really do these kind of manipulations if we don't arrange it so that F is disjoint from both the components of A and the components of N. Not disjoint, but this is distinct from the components of A and the components of N. Okay, so now the hard part is figuring out exactly what N is going to be, what F is going to be, what delta and E and A are going to be. And how they include this roundup of G in this case that we have floating around. Okay, so the first step is some setup. Basically, without loss of generality, we can assume that AD minus kx minus g is ample instead of just big enough. So in our assumptions for the theorem, we're assuming it's big enough, and our first step is just that we may as well take it to be ample. And the way to do that, we're going to take a resolution and then perturb the coefficients. This is the kind of this general general idea that if you take a log of resolution and you perturb by some f exceptionals to make big enough divisors ample. So let f from x prime to x be a log resolution. And let's write f upper star kx minus g let's write it as kx prime minus g prime, where g prime is the divisor satisfying that f lower star g prime equals g. So basically, let g prime be strict transforms plus exactly whatever exceptionals you need to make this equality true. Okay, so now the discrepancies of p over x minus g are the same as those I'm not sure why this Apple Pencil keeps disconnecting. Are the same as those x prime minus g prime. This was one of the first maybe exercises we had about discrepancies. And so that tells us that x prime minus g prime is KLT. And right, so then we write a f upper star d minus kx prime minus g prime. This is just a pullback of our big NF divisor. I'll just drop the parentheses for now. The reason I was writing that before was just to emphasize that it's kind of the same statement that you're looking at, divisor minus the log canonical, whatever your log canonical divisor is, but I'll just distribute that minus sign now. So this is big enough. Because the pullback under some birational map of a big enough divisor. And so now we pick some small f exceptional effective, say E is equal to sum of Pj Ej, and we'll be doing this all over the place in this proof, just like we did last time. Such that this pullback of this big NF divisor minus E is ample. Okay, so now let's just define G double prime to be G prime minus F. So now this difference, this is the same as AF upper star D minus KX, sorry, E, minus KX prime plus G double prime. And on the other hand, like G prime is G double prime plus exceptionals. And so the sections don't change. So so if we look at the sections here, these are, well, I'm twisting up, so they're contained in the sections on G prime, and then these are the same as the sections on X because I'm just pulling back. Okay. So if we can show that under the extra assumption, actually here we really did two things. We showed that it suffices to assume that our divisor is ample rather than just big enough. But also X prime is actually simple normal crossings. So actually in step one, without loss of generality, we can assume that this is ample and that X comma D, X comma G minus G is S and Z. Okay, so that's step one. Step two is just to throw out a kind of corner case that is not so relevant. So suppose that D is numerically trivial. Then in this case, G is the same as just Kx plus A, where A is ample. That's just rewriting our equality when we plug in that D is actually numerically 0. And so we get that. And of course, okay, so we get that H0x MD plus the roundup of G. That's the thing we want to show is not 0. This is equal to just the Euler characteristic by KV vanishing, because our divisor is numerically equivalent to Kx plus an ample. So in fact, here it's really Kodaira vanishing. Because we're really in the simple case. I guess I'm rounding up though, so I really should say KV. If I wasn't rounding up, then it would be Kodaira, but because I'm rounding up, I guess it's really KV vanishing. But then this is equal to the Euler characteristic of just G by Riemann-Roch. Right? It doesn't really matter what the formula for Riemann-Roch is. The fact that there exists a Riemann-Roch formula tells you that the Euler characteristic depends only on the numerical class. So MD plus the roundup of G is equivalent to the just the roundup of G. And then again, by KV vanishing, because G is still an ample divisor with S and C support, then this is equal to H0 of the roundup of G. But now we go back to our remark. So our remark was that under the assumptions that X comma minus G is KLT, that tells us that the roundup of G is effective. So this is not equal to 0. So that was the simple case where all the sections just come from G, D doesn't contribute anything. So from now on, we can just assume that D is not numerically trivial. So in particular, there exists some curve where D dot C is not 0, but D is also Neff. That was one of the assumptions of the theorem. So that implies that there exists a curve, an actual integral curve C in X, such that D dot C is strictly bigger than 0. So that's the important thing about step 2, where we reduce to the case where we have some curve that hits D strictly positive. Okay, maybe it's a good place to pause for questions for those first 2 steps. Okay, so now we want to pick some divisors and some resolution so that we can write this expression with all those properties that we wanted. And if you remember from last time, the way we did this was by writing down an expression for this n in terms of some b and some c. And then we had to pick some coefficients to single out a specific f, a single f as a divisor, and those it's like this f is going to be like the only divisor with discrepancy exactly -1 when we wiggle things around. And to do this, we had to set some coefficients to be the minimum of some expression to get that there was exactly one, to pick out this f that had coefficient exactly -1. It needed to be the minimum because we want everything to be at least a log canonical pair, but we wanted everything else to be this KLT piece, this delta y, or this effective piece. But to do this, we needed to like use the moving part of D and then use the fixed part of D and kind of wiggle coefficients around. And here we have to do a similar thing, but how we're going to do it here to kind of make this minimum work out correctly, we're going to pick a specific resolution, or we're going to pick a resolution that factors through a specific blowup so that we can control the discrepancies of one of the divisors, so that then we can control the minimum of our coefficient set to get everything right. And so to do that, we want to pick some resolution that factors through a blowup that we like. So pick some point that's just away from G. And we're going to blow up this point, and we're going to add some divisor whose pullback, like whose multiplicity with the exceptional divisor, we can control so that we can get the right coefficients in our expression. But that's why we're picking it away from G, so we don't have to worry about the singularities of G. We can just add whatever divisor we want that has the right multiplicity. So the claim is that there exists a divisor that's in the linear series that we care about. It's in the linear series that we know something about, with high multiplicity at this point. Maybe I really should say, well, let me finish writing down and then I'll say what I really mean, because I didn't say what Q is. So we'll say that for all Q large enough, the claim is that we can find a divisor whose multiplicity at this point is large. And so then we'll split up in this expression. We have this kind of pullback. Like once we replace K with the pullback of KX and the discrepancies, then we'll have like the pullback of AD minus K plus G in this expression, and we'll split that up into some contribution that's just whatever it is, and then some contribution coming from this M with high multiplicity that we've picked. That's why we wanted M to be of the form QD minus KX plus G. And this will let us control the minimum of the coefficients that we need to take. Okay, so how do we justify this claim? So let's just write D for the dimension. Then we had this lemma about Neff divisors. So I'll just write since D is Neff. Then we had this lemma some time ago that said that the intersection of D with any multiple of an ample is non-negative. So and so if we look at the intersection of this QD minus KX plus G, we can ask how does that grow? How does that number grow? And the reason we care about that number is because we want to produce sections, and so we want to use Riemann-Roch to produce sections. So if we look at QD minus KX plus G, the top intersection to the dth power, then this is going to be, well, let's split it up as Q minus AD plus AD minus KX plus G to the D. And now for Q large, specifically for Q larger than A, but we might have to take later, we're going to increase Q even more. For Q large, then this term is Neff because D is Neff, and this term is ample because of step 1. And so by this lemma, that tells us that this whole quantity, all its terms are non-negative. Let's just pick out one term that we're going to use. This is all greater than the kind of the second term, the linear in D term, which is that. Okay, where that's intersection product. Okay, so this self-intersection is greater than or equal to this particular product. And now we'll use our observation that there exists a curve where D dot C is actually strictly positive. And since this stuff is ample, then kind of we can pick hyperplanes. So because this is ample, then maybe up to taking some large enough multiple of our ample, so it becomes very ample, we can pick hyperplanes so that our intersection of our hyperplanes is C plus some effective stuff, which is basically just saying that any curve is contained inside of a complete intersection, because basically you multiply your ample large enough to make it very ample, and then if you keep making it bigger and bigger, there are going to be a lot of sections that vanish along your curve. You take the intersection of enough of them so you get something one-dimensional. It might not be C, but it'll be C plus effective stuff. And then we'll just divide. Since we have to make everything a high enough multiple, we'll just divide again because we only care about numerical computations. So that implies that we can write some expression for AD that up to numerical equivalence, this AD minus K plus G to the D minus 1 can be written as some C prime plus E, where D dot C prime is strictly bigger than 0. So C prime is just some multiple of C, and E is effective. And again, this is where we use that D is not numerically 0. So that tells us that this is strictly positive. because d dot c prime is strictly positive, d dot e is greater than or equal to 0 because d is an f. And it doesn't just tell us that it's strictly positive, it actually tells us that as q goes to infinity, this whole thing goes to infinity. Because we have something non-negative times this q term. Okay, so then we write down what asymptotic Riemann-Roch says, which we briefly used before, but you can just believe me. So asymptotic Riemann-Roch says that the space of sections then, if we write it down as a polynomial in this coefficient, so t times whatever our divisor is, in this case is qd minus k plus g, it's going to be greater than or equal to, let me just give some notation here. Let's call this term that we just showed goes to infinity. Let's call it n of q. So asymptotic Riemann-Roch tells us that the space of sections is greater than or equal to t to the d over d factorial times n of q plus some lower order terms. So this gives us that, it tells us that there are a lot of sections for this large enough multiple of qd minus k plus g, but it tells us exactly how fast they grow. On the other hand, we can ask, how many conditions are you imposing to make the multiplicity at least 2 dim x? Well, x is smooth. That was our reduction in step 1. And so having multiplicity greater than 2 dim x is like saying that all the monomials, if you take coordinates around x, then you want all the monomials of smaller degree to vanish in the expression that cuts out m of q. Everything's Cartier here. And so that gives us, that implies that the codimension of the locus of divisors with multiplicity greater than 2 dimension, except we don't just want 2 dimension here, because here when we talked about the space of sections, we got something asymptotic, or we have a t. So eventually we're going to need to divide by t. So if we want, because we want something that's just in qd minus k plus g. So if we want the divisor we get after dividing by t to have a multiplicity greater than 2 dim, then we need to put a t here. So the codimension of the locus of divisors with multiplicity at least 2 dim x times t is, or grows, like t to the d over d factorial 2d to the d, because that's how many conditions we need to impose. And so that tells us that so that tells us that the dimension of the space grows as the difference of these two. But this 2d to the d is a constant. It just depends on the dimension. While this q, if I make q larger, n of q goes to infinity. So I can just make q large enough so that it's bigger than 2d to the d. So for both q and t large, this difference becomes large, and that tells us that there are sections with the multiplicity condition. So that implies that we have sections M that depend on q and t in t times q d minus k plus g with multiplicity greater than 2 dt. And so then when we divide, if we just let m of q be the q divisor mqt over t, now this is a member of qd minus k plus g, and it has multiplicity greater than 2d. And I guess I really, because we're dividing, I really shouldn't say that it's in this linear series, because that's being in a linear series is like using rational equivalence. It's really q linearly equivalent because I'm dividing, so I can really just say that, or maybe for all our arguments, it's good enough to just say numerically equivalent, because all our statements are insensitive to numerical equivalence. All our hypotheses, at least. Okay, questions about that step? Okay, and so now we're gonna pick a log resolution that factors through the blowup of this point, and we're gonna write everything in terms of this m and other stuff, and then use this multiplicity condition to bound the coefficients in one of our exceptionals. So step 4. Pick some log resolution. It'll depend on q because m depends on q, but we'll just suppress that dependence on q. Pick some log resolution of x comma g plus this new divisor m of q. So of course, x comma g was already simple normal crossings by our step 1, but now we have this extra m in there. So we want to make that s and c as well. And in particular, because m has this large multiplicity at this point, this f has to factor through some blow up at that point. Let's just assume that it factors through just the usual blow up. So maybe, a priori, if you want to resolve, maybe you can blow up some higher codimension loci through that point. But let's just say that we pick a log resolution that actually factors through just the usual blow up. Okay, and now let's just write down all the divisors we have on this log resolution. So we have our discrepancy formula. Where these coefficients are bigger than -1 by our KLT assumption. And this sum of Bj and Fj will include both exceptional divisors and strict transforms of the divisors in G. And then we have the divisor that we know is big in F, which is our pullback of AD plus G minus K. This is our big NF divisor. And so now we'll perturb it such that this is ample. But to make all the numbers kind of work out right, we're just going to put a 1/2 here. Of course, if we put 1/2 in front of this first divisor, it's still big enough, so we can still take some perturbation to make it ample. We'll just throw that in there. And this 1/2 is really going to be related to this multiplicity bound that it's 2D. But in the end, you just need something to get the right bounds. And then 3, let's write down f upper star m of q. let's write it down. So it's some normal crossings divisor. Let's index things so that it has one component R0, F0, which is where F0 is the exceptional of the blowup over X. And then whatever else is left, we'll just call it RJ, FJ for whatever's left. And so our setup tells us that R0 is greater than 2D. Because we picked our M of Q with this condition. Okay, and in these divisors, the point is that in all these expressions, sum of BJ, there's going to be some exceptionals and some strict transforms, and you kind of have to keep track of what does the coefficient look like if F is an exceptional divisor versus what does the coefficient look like if F is not an exceptional divisor. And this came up already last time. Okay, so now we're ready to write down our linear combination of all of these divisors to produce our N and our A in our strategy. So let's remember again what we're looking for. We're looking for an expression like ky plus delta y plus f plus n well, delta y is a boundary, f is integral, n is ample, e is effective, and exceptional. Sorry, effective and exceptional. So this is the type of expression we're looking for. And so now the claim is that if you play around with it, that this particular linear combination works. Or maybe I should say, you guess a linear combination like this, and then you find the B and the C that works. Yeah, that's a better way to say it. And this is exactly the same as kind of where these Fs came from and what exactly are the Rs and the Ps. And the Bs were different in the proof of base point free, but once we got to this point where we had a resolution and we wrote down these divisors, then the expression we wrote for n was essentially the same. So we write down an expression like this, and we want to find the B and the C, the range for B and C that make it ample. And so to do that, we can rewrite this as, so here we have this, right. We have this minus ky, and then we have these bjfj's. So there's our discrepancy. So if we look back at ky equals f upper star kx minus g plus the sum of bjfj's, then those terms we can combine to get the pullback of just kx minus g. So we get this whole thing is f upper star bd minus kx plus g. What do we have left? Well, we have the p's left, and then we have the c times rj's left. So c times rj, that came from pulling back m of q. So here we have minus c times the pullback of m of q. And then the p's were just whatever they were, this small perturbation to make things ample. Okay, and now we use that m of q is numerically equivalent to qd minus k plus g. So this whole thing is numerically equivalent to f upper star of bd minus kx plus g minus c times qd plus ck minus cg plus our perturbation, or sorry, minus our perturbation. And then, okay, we rearrange some things around. Let me just skip a few steps. So basically, we put together the terms with d's, and we put together the terms with k's and g's. But right, so but we separated because what do we know about? We know about ad minus k plus g. So we want to separate out an AD from everything. So when we do that, we get F upper star B minus CQ minus A times 1 minus C. Okay, we get some expression, whatever it is. Trust me that the arithmetic works out. Plus 1 minus C AD minus K plus G. That's the thing we care about, or that's the thing we know about. That's what our hypothesis tells us about. Plus our perturbation. And now we look at this and we say, okay, we want n to be ample. So what do we need? Well, right. So we need to go one step further, because where is our ampleness coming from? It's coming from 2. And in 2, we put this 1/2, which of course at this point, it's not clear why we should have a 1/2, but we know that we want to include some portion of this 1 minus C AD minus K plus G to give us positivity. So might as well use 1/2. So then here we get, let's just split it up as F upper star, this large expression, B minus CQ minus A 1 minus C D plus 1/2 minus C AD minus K plus G, and then plus, let's pull out the rest of it, 1/2 F upper star AD minus K plus G minus our perturbation. Okay, great. So now we're in business. So this term is ample. This term, that's big enough as long as, or in fact, even ample, as long as C is small, as long as C is less than 1/2. But then we're pulling it back. I forgot about this F upper star out here. So this term after pulling back is big enough. And then this term is nef as long as whatever the coefficient is non-negative. So to make everything work, we need, so then we have nef plus big enough plus ample. So the whole thing n is ample if C is less than or equal to 1/2, and B is greater than or equal to yeah, you do some extra arranging here. Let me just skip that step. So it's greater than or equal to A plus C times Q minus A. Okay, great. So again, here we need this coefficient to be greater than or equal to 0, and this coefficient to be greater than or equal to 0. Okay, so we have our n, this expression, and now we're close to getting the expression we want, because we see that we have the BF upper star D, we have the KY. Now we just need to guarantee that this sum of these F's splits up in the way that we want it to split up. Splits up as a single component. Now we've moved everything over, so it's a, wait, how we moved everything over? Yeah. No, yeah, so we want a single component with coefficient 1, and then everything else to be a difference of KLT boundary and effective exceptionals. So that's what's left to do here. Okay, so to do that, we need to pick the right C. So we'll let C be the minimum of 1 plus Bj, these are these log discrepancies, minus our perturbation, which is some epsilon, over Rj. So BJs were bigger than -1, so 1 plus BJs are bigger than 0. PJs are infinitesimally small. RJs are non-negative because the coefficients are strictly positive because the coefficients are the pullback of an effective divisor. So this whole thing is bigger than 0. And it's exactly what we need to just, cancel out this C term there for the smallest one. And so pick, just like before, we pick our perturbations, Pj generically, so that this minimum is achieved exactly once. Say for the coefficient some particular j, and we'll call that f. So f is this index where this minimum is achieved. And so now f is some irreducible divisor because everything is simple normal crossings, and we're assuming that this minimum is achieved exactly once. And so that this f, well, what is it? It's exactly the divisor appearing in this expression. I don't know what a good term for this expression is, but it's exactly what's appearing in this expression with coefficient exactly 1. So that's going to be our f there. Okay. But now we need to check that this minimum is actually less than 1/2. And that's where all the work that we did really comes in. That's why we needed to pick this M of Q to write things in that had this high multiplicity at a point, make sure our resolution factored through that blow up, because that's going to make sure that our minimum is actually small. And so what's the upshot? Well, if we look at the coefficient B0, this, if you remember, F0 was the exceptional divisor over X, was the exceptional we got from blowing up. So for that one, we have this, that R0 is greater than 2D. And what's the coefficient of that divisor in the discrepancy? Well, that's the computation of blowing up a smooth point on a smooth variety. Sorry, just blowing up a smooth point. And here we use the assumption that X was disjoint from G. So here it's just blowing up the point. We don't have to worry about G. B is just what it is when you just blow up the point. And that was an exercise. Well, I guess the exercise is more general, but as part of that exercise, we get that this is D minus 1. That's the discrepancy you get when you just blow up a smooth point. And so this is D minus 1. R0 was greater than 2D by construction. And so we get that C is this minimum, so it's less than or equal to whatever this term is for these particular B0 and R0, because the minimum of them. D minus 1, we get just D. So we have D minus some epsilon, whatever P0 is, just some small number, divided by 2D for our R, and this is strictly less than 1/2. So we have guaranteed things so that if we take our minimum, so that there's a unique F with that appears in coefficient 1, we're still in the case where n is ample, because we're still inside of this range where C is less than 1/2, which is what we needed for our way of writing down n. And so now essentially we're done. Now we write down our strategy. So we had n of B C equals B F upper star D minus KY plus this sum as A minus F, where F is our single term, and then A is just whatever's left. All the coefficients of A are strictly bigger than -1. And so that tells us that the roundup of A is effective. Also, we can get, because we kind of like F, like, what do I want to say? Like the coefficient of the divisor F in this sum is exactly -1. So it's not like we're just taking out a -1 and then there's still some component of F. That's it. There's no more in this A. There's no more. There's nothing supported on F anymore in this A. So that was the other thing we needed. That F didn't share components with our N. So we've guaranteed that. And so now ky plus our ample plus this f is equivalent to bf upper star d plus a, where a is this thing whose roundup is effective. But now we need to compare everything to the roundup of g. And so let's write down the pullback of g as sum of gj fj. And so if fj is not exceptional, then the coefficient gj is actually the same as bj, because the discrepancy of a non-exceptional divisor is just minus the coefficient. Our boundary, or our pair is x comma minus g, and so the discrepancy is just g for a non-exceptional divisor. So that tells us that so then we look at this a. What are the coefficients of a? Well, the coefficients of a for the same divisors are like minus c rj plus bj minus pj. This minus perturbation, and then we also have this minus c rj that's strictly bigger than -1, because f was the only divisor with coefficient exactly -1. So this whole thing is less than bj, which is gj, and so when we round up, we get that the roundup of a is less than or equal to the roundup of g plus some exceptional stuff. And because everything's effective, that's fine. So let me say it again. In this A, we have some divisors that come from exceptionals, and those, whatever, they're just some effective exceptionals. Those don't change sections, so we don't care about them. And then we have some divisors that aren't exceptional, and those are the same divisors that are not exceptional in the pullback of G, but with smaller coefficient. And so A is effectives, is a roundup of A plus effectives is equal to roundup of G plus effective exceptionals. That's another way of saying this. And so now H0 of the pullback of D plus the roundup of A is contained in H0 of the pullback of D plus, and here I forgot the F upper star, so of course G is downstairs, plus the pullback of the roundup of G by this observation, where here I'm using that these exceptionals don't contribute sections. Again, this negativity lemma again. So really what I should have written is that H0 with this roundup of A is contained in H0 with the pullback of the roundup of G plus whatever these effective exceptionals are, but that equals the sections on this pullback. And then because we're pulling back this divisor, this is the same as the sections downstairs, and that's the thing we want to show is not zero. Okay, so it suffices to show that this BF upper star D plus the roundup of A has sections. And now we use our induction. So by KV vanishing, if we look here, KY plus this ample plus this integral F, just apply our strategy. So by induction, the sections of this divisor surject onto the sections of the restriction. Everything restricted to F. And then on F, BF upper star D plus the roundup of A restricted to F is equivalent to KF plus N BC restricted to F, where now this is ample plus S and C, because the restriction of S and C to S and C where we don't share components, and so this has sections by induction.